to talk about the gas laws quiz. I don't think I wrote it on as many papers in here as I did in the other class, because I said it before the quiz. Please, please, please rearrange. On the test for this chapter, and it is a tiny little test, it's really a big quiz / small test, you need to write the equation, write the rearrangement, and list your variables. Like, I expect you to be able to do that. And especially if you're going on to physics next year, I beat you with the stick of writing your equation, showing your rearrangement, and writing your variables, because there are no options there. So, starting with number 1, all we needed here was P1V1 equals P2V2. And when we rearrange to solve for P2, we get P1V1 over V2 equals P2. Listing variables is important. It's easy to keep track of in a problem this size. When you get into the bigger problems, it becomes harder to keep track of things. And so having a list of your variables is a nice visual technique for not screwing up which one was the initial and the final volume. So 90.0 centimeters, and we're curious about P2. So now we've got our rearrangement, we've got all of our variables listed, we can just plug in. And I also recommend, implore, demand, that show the equation with everything plugged in. Does it take a second of your time? It does. However, you don't have any place else to be right now. Be here now. Embrace the chemistry. So just take that extra second. Like, I know I had 1 or 2 people who had mistakes where their rearrangement looked good, their variables were listed, and then they had the wrong answer, and I can't see what happened. I can't see if you plugged something in wrong, wrote something down wrong. Earlier today when I was doing this one, I couldn't read my own writing, and I typed in 27.5 instead of 22.5. So, write that rearrangement and then write your plug-in. We get, for this, a raw answer of 38.75 kilopascals for our final pressure. And we only have 3 sig figs to work with if we go back to our originals. So this ends up as 38.8 kilopascals. Easy for me to say, is our final pressure. So most people did okay on that one. A few sig fig errors, but that's fine. Number 2, we're dealing with volume and temperature. So this is a volume temperature problem, and because I'm evil, I'm asking you to solve for T2. It's in the denominator, which means that it's tricky. To do that, you can do the cross multiply and then solve, and that may be less objectionable to some of you than trying to rearrange everything. So that gets rid of our V1, and we're left with T2 equals V2, T1 over V1. List variables. Our initial temperature is 67 Celsius, which is, of course, 340 Kelvin. Our initial volume is 150 milliliters. Our final volume is 50.0 milliliters. And what we want to know is, what temperature is that volume going to be? At what temperature will that volume occur? So we've got our rearrangement, we've got our variables listed, and so we're ready to go. T2 equals 50.0 milliliters times 340 degrees Kelvin over 150 milliliters. We get a T2 of 113.333 on into infinity Kelvin. We only have 2 sig figs to work with, so we have 2 options for listing T2. We can say it's 110 Kelvin, or we can say it's a negative 160 degrees Celsius. Either of those have 2 sig figs. If you're going to do the conversion to Celsius, do it from your raw number and then sig fig your answer. Don't take sig figs until the very last thing ever. Okay, number 3. Woo. So we're dealing with pressure and temperature. And so we know we're using P1 over T1 equals P2 over T2. And so rearranging to solve for T2, we have T2 equals P2T1 over P1. There's just one problem. When we go to list our variables, they seem to be rather thin on the ground. So really the only variable we get is T1, negative 73 Celsius or 200 Kelvin. We're not given P1. The only thing we're told is that P2 is twice P1, and that's all we need. And then we're looking for T2. So using this, we can write the following. T2 equals, well, P2 is equal to 2 times P1. 2 times P1 times T1 over P1. What happens as if by magic? Whoop, whoop, those go away. So you're writing the relationship between the initial and final pressure. So T2 then equals 2, let me clean that up, equals 2 times T1. So once you see it that way, it's pretty simple. I will tell you that I always throw a couple of these in. You know, the volume is tripled, the pressure is reduced by half, the temperature is multiplied by a factor of 4. It's good brain training for algebra, and if you're going to take physics next year, we do a lot of things where you have to be thinking in terms of expressions and substitution. So it's good practice. And once you've seen a few of these, you don't miss them anymore. Okay, so then T2 equals 2 times 200 Kelvin. T2 equals 400 Kelvin. Now, we have, and that's 127 Celsius, but we have 2 sig figs. So there are a limited number of ways to show that. We can either say that it's 4.0 times 10 to the second Kelvin, or it's 130 Celsius. So yeah, it does say it in Celsius, so I forgot that I wrote that. So you have to give it as 130 Celsius. That's the only way to give that one as 2 sig figs. Okay, the last two, the ones on the back, are the big ones. Okay, so we have a weather balloon launched from sea level. Pressure at the launch site is 772 torr, that's millimeters of mercury. And the volume of the balloon is, the volume of the gas inside the balloon, I should say, 4,400.0 liters. The temperature of the gas is 30 degrees Celsius. That should have had a decimal behind it. I screwed that up. So really, technically, looking at that, you only have 1 sig fig, which is pretty crazy. But if you did that with 2 sig figs, I didn't knock you for it. So this thing is going to go to the top of the atmosphere. The stratosphere is near space. And at the top of the atmosphere, up in the stratosphere, atmospheric pressure is really close to 0. You're at a point where you have very, very low pressure. This is less than 1 torr. 760 torr is normal atmospheric pressure at sea level. So this is, you boiling away territory. It's also really cold up there because there aren't a whole lot of gas molecules to maintain any sort of heat. So the temperature is negative 82.5 degrees Celsius. So let's get these into Kelvin. We have 303 Kelvin, and we have 190.5 Kelvin. Okay, so we've got everything. We are solving for V2. Not difficult. You can do your cross multiply and divide trick if you want. P1, V1, T2 over T1, P2, however you get there, equals V2. So now it's just plug and play. It's plug and calculate. And so what we get as a raw answer is 270,3306.179 liters. And if we put that with 2 sig figs, that's 2.7 times 10 to the 6th liters. 1 sig fig would be 3 times 10 to the 6th liters. Either way, the fact is this puppy is going to burst with a vengeance. And if you've ever actually seen imagery of a weather balloon launching, these are not like latex balloons. They're not stretchy. They're typically made of mylar, which is the shiny stuff. And when they launch, they look like they're tragically underinflated. They're like an elephant that's lost weight. They've got all this loose balloon hanging down around them, and they look really sad. They do that because as they travel to the upper atmosphere, the gas inside the balloon expands dramatically based on atmospheric conditions. So somebody at the National Oceanic and Atmospheric Institute is doing these calculations. So in this problem, somebody at NOAA just got fired because those weather balloons don't come cheap. I think if you screw up your calculations and it goes pop, you have a world of hurt visited upon you. So this is a real life scenario in looking at different, changing conditions and how a gas will behave. Okay, let's look at the next one. Okay, so again, we're dealing with all three factors: pressure, temperature, and volume. And here we've got a sample of gas that's being put underwater. So underwater, the pressure on those gases is higher than it is out here in the atmosphere where you and I are. It also tends to be real cold down beyond a certain point. So, here we're 1,500 meters below sea level. That's well below the point when light can penetrate. So it's going to be cold and dark and a high pressure environment. What we want to know is what happens to that sample of gas. So we can do rearrangement via whatever method you would like, but we get this for our rearranged value. Then it's just plugging in. So we have this as our plugged in expression, and we get a raw answer for V2 of 414.520633 milliliters. We have, if you ignore the fact that I screwed up here, it looks like 2 sig figs in this problem. If I had remembered to put the decimal there, sorry. So with 1 sig fig, which is actually what's really shown there, your final answer would be 400 milliliters. With 2 sig figs, if you ignore what I didn't mean to do, it's 410. So that's your final volume. Big things. Please, please, please write the equation, write the rearrangement, list your variables, show the plug-in. Like I said, yes, it's a few seconds of your life, but it's not like you have someplace better to be, or someplace better that you can legally be. So, yay, it's our little chemistry party. Questions, comments, or concerns on the quiz?